Hi everybody. In this video I'm going to talk about still rigid bodies, but now we're going to talk about angular momentum. So last time we talked about the moment of inertia tensor, but remember that angular momentum, classically the way you've done it before, we've written it as it equals the moment of inertia times omega. You know, the translational equivalent is just regular momentum, which is mass times velocity, but when you're in rotational motion, you have angular momentum, and the mass is replaced by the moment of inertia, and velocity is replaced by the rotational velocity. So we would usually write angular momentum is the component in the x direction plus component in the y direction, which I'll call x2, and then x3, which would also be then, I'll leave it at that. But now we have our components of our angular momentum are going to be written like this. So the ith component, now we have this matrix, this tensor for moment of inertia. So this is going to be our angular momentum, and your author in your book goes through and shows you how you indeed get this, but I think we'll skip that derivation for now. But you'll see this written as a vector sometimes like this, I dotted into omega, where these are our usual, what we call three-dimensional vectors, and this is a second-rank tensor. Although, as you already know, that these vector, what we call vector, is a first-rank tensor. Okay, and then our torque, which your author in your book labels as n, we know that torque is equal to a change in angular momentum with respect to time. So that's going to be our torque. Okay, so we got this tensor that is a three by three matrix. We can write it as I11, I12, I13, I21, I22, I23, I31, I32, I33. Now, for certain axes, now remember we did, for example, we found the moment of inertia tensor for this triangle. Where here was our axis of rotation coming out this direction. This was x, this was y, this was z, and it was rotating around this. So we found a moment of inertia tensor relative to this axis of rotation. We could have picked for this picture, maybe we could have put one of our axes this way and one this way. We chose to have the axes a certain orientation. So how you pick your axis is going to, your moment of inertia tensor is going to depend on that. So for the right choice, you could get your moment of inertia tensor to be diagonal. I11, everything else is 0. I22, I33. And if that's the case, then what will your angular momentum be? Multiply that by your omega 1, omega 2, omega 3. Well, it'll be I11 omega 1 plus I22 omega 2 plus I33 omega 3. So it simplifies. And when you can do that, when you can get these to be, this inertia tensor to be a diagonal matrix, then the axes that you picked And you remember, omega 1, omega 2, and omega 3 depend on those axes. You have omega written in terms of those axes. Omega 1, E1, plus omega 2, E2, plus omega 3, E3. So when you pick your coordinate system, you find your components of omega. But then if you can get the moment, if the moment of inertia tensor ends up like this, then the axes that you've picked are what we call principal axes. Oh, I forgot to put E1, E2, E3 here to make these a vector. So when this happens, you picked what we call principal axes, plural, I guess, here. Okay, and it just simplifies things. So let's take a look at an example of that. Okay, for example, let's just take 3 masses, and this one is on the x-axis at A, this one is up 2A on the y-axis, and then you come out along the z-axis 1A, and this one is you go along the z-axis 2A, and then up A in the y-axis. And let's say this is a rigid body, so somehow they're connected so they don't change positions relative to each other. So first, let's just find the moment of inertia tensor and see if I've chosen principal axes. If not, let's try to find the principal axes. Okay, so I'm going to show you with this example how to get the principal moments of inertia, and then once you have those, how to find the axes that go with those. Okay. All right. So, and I'll just tell you now how we get the axes is we find the relationship between omega 1, and then this will be our principal axes 1, omega 2, omega 3. So we'll say, boy, we could write that like this. And we'll look at the relationship between omega 1, omega 2, omega 3 and deduce what E1, E2, and E3 must be. Okay? So our first step is actually to find the moment of inertia, and now we have discrete particles. We don't have a continuous rigid body. So we go back to our definition of the moment of inertia components. If you write it discretely, we wrote it like this: m alpha. Alpha is however many, 1 to n. And then we have this delta function ij, the Kronecker delta. Then we have the sum xk for this alpha. K equals 1 to 3, and then minus x I alpha xj alpha. So that was the general form. From this, we find, for example, if we wanted to find the 1, 1 term, that Kronecker delta would be there, and we'd have x1 squared plus x2 squared, oh, this is squared, plus x3 squared. Sorry there. Minus x1 squared. So it would cancel out the other x1, so we would have this x2 for that alpha squared plus x3 squared. And if we had I22, it would be sum of the masses x1 alpha squared plus x3 alpha squared, and so forth. Now, when we have the I is not equal to j, if you remember that, for example, I12, the Kronecker delta goes to 0, we'd have that negative sign and bring it out front, sum of masses. So we're doing a sum still, and then we'd have x, I is 1, alpha, 2 2 alpha. Okay? So, let's find the moment of inertia tensor, and then we'll figure out how we diagonalize it. If it's not already diagonalized, maybe these are the principal axes. So let's find I11. Now, all these masses are the same. I didn't tell you that. And I'm going to call this particle 1, this one up here particle 2, and this one particle 3. So I11, I'm going to sum the masses. Mass 1, x, excuse me, x1 is going to be x, x2 is going to be our y, and x3 is going to be our z. Okay? Excuse me. So, I'm going to have the first mass, and this is the y squared for it, for mass 1, alpha's 1 mass 1, squared plus z1 squared, plus the next mass, and so then y for mass 2 squared plus z2 squared, plus mass 3, y3 squared plus z3 squared. So they all have the same mass. So I have mass, now y1 is 0, z1 is 0 for that mass. For mass 2, y for it is 2a squared, plus, and the z for it is a squared. For the third mass, same mass. Y for it is a squared, and the z for it is 2a. So I have two of these. This one's 0, this term. So I have 2m, and that's 4a squared plus a squared. So I get 5a squared. So this is going to be 10ma squared. Let's do another one. Let's do I22 equals. So again, the delta function is going to be 1. So this is going to be, I'm going to use this form here, sum mass alpha, and then I'm going to have x, oh, this is for the 2, so I'm going to have x1 squared. So that's going to be the x. I'll just write it like this right now. X for mass alpha squared plus z for the alpha squared. So that's going to give me mass 1, x1 is a squared. The z squared for it is 0. Plus mass 2. For mass 2, x is 0. I made a mistake here. This is a plus here, not multiplying. So that's plus. For mass 2, x is 0, but z is a. And for mass 3, this one, x is 0, but z is 2a. So they all have the same mass, so this is ma squared plus ma squared plus, this is a 4a squared, so plus m 4a squared. So 4, 5, 6, 6ma squared. So let's do one more. Let's do an off-diagonal one. I'll just go up above here and do it. Let's do yz. So that would be 2, 3. So that's going to be negative sum mass of alpha x2 alpha times x3 alpha. So that's negative sum of mass alpha. X2 is y and x3 is z. So there we go. So this is going to be for mass 1. I'll put mass 1, y and z are 0 for it, plus mass 2. Y for mass 2 is 2a. The z is a, plus mass 3. The y is a, the z is 2a. So now I get negative, they all have the same mass, and then I have 2a squared plus 2a squared, so I get 4a squared. So negative 4ma squared. And we could go on, but to save time, I'm just going to write the final result. So I is going to equal, we found I11 was 10ma squared. It turns out I12 is going to be 0, I13 is 0. What other one we found? I22 was also, no, it was 6ma squared. It turns out I21 is going to be 0. What else we found? We found I23 to be negative 4ma squared. And then to fill in the rest, we're going to have 0, negative 4ma squared, and 6ma squared. So that's our moment of inertia. Excuse me. So that's obviously not a diagonal matrix. So how are we going to find the principal moments of inertia where we diagonalize this and then find the axes that go along with that? Because if we find the right axes, remember, then we can write L is just I11 omega 1 plus I22 omega 2 plus I33 omega 3. So that's what we want to do. And all the I12s, I23s will be 0. All the off diagonals. So here's what we want to find. We want to find, in general, this times omega 1, omega 2, omega 3. We want that to be a diagonal, and I'm just going to write lambda. So we want to find we want this to equal this. So we would, if I subtract this side from this side, we should get 0, and I'll write that as this. So what we'll have is this I11 minus lambda. So we'll find the lambdas that will give us, we'll make this so. So now we need to solve this for the correct lambdas. Okay, so here's this, and we'll have this minus lambda, this minus lambda, this minus lambda times omega 1, omega 2, omega 3 equals 0. Now this will have, if you go back to your studying your linear algebra, which we are not doing in here, But this will have a non-trivial solution if the determinant of this is 0. So we need the determinant of this to be 0. I made a little mistake here. This should have been, since I put omega 1, omega 2, omega 3 here, I should have had omega 1, omega 2, omega 3 here. So, sorry. So the determinant of this matrix we want to be 0. So so what is that going to be for us? That's going to be, write it down here, 10ma squared minus lambda. We had 0, 0, 0, 6ma squared. This stays the same, negative 4ma squared, 0, negative 4ma squared, and then another 6ma squared minus lambda. So we want that to equal 0. So if we start doing that, this gives us 10ma squared minus lambda times 6ma squared minus lambda times 6ma squared minus lambda. And then the rest will be 0 in that direction. If we go in this direction, we get this, negative 10ma squared minus lambda, negative 4ma squared, and another negative 4ma squared. So there that is. We need to do a little bit of algebra. I can pull out a 10ma squared from both those terms, and then I'll have left here 6ma squared minus lambda, the squared, minus 4, minus minus, that'll make it a positive, but I have this minus sign, 4ma squared squared. It's going to give me 10ma squared minus lambda times 36 m squared a to the 4th minus 12 ma squared lambda plus lambda squared, and then minus 16 m squared a squared. This will be a to the 4th. So this is a quadratic equation. Obviously, one solution, which I'll call lambda 1, is going to be 10ma squared. This would make the whole thing equal to 0. And then what's in these brackets, if we set that equal to 0, that quadratic equation, you get two solutions, and I'll just write them down. One solution is 10ma squared, and the other solution I'll call lambda 3 is 2ma squared. I won't go through that, but I encourage you to check that. All right, so now I have my solution. So now these are my principal moments of inertia. So my principal moments of inertia are 10ma squared, 0, 0, 0, 10ma squared, but I need the right axes to find that moment of inertia. Remember, the moment of inertia, how you calculate it, depends on your axes. Let me go back to this. I found that moment of inertia by using this set of axes, but now we want to find a new set that would give us the principal moments of inertia that we found. All right, well, I told you we're going to look at the relationship for the omegas. So how am I going to do this? I'm going to go back to this equation equal to 0, and I'm going to put in my lambda 1 and see what the relationships between omega 1, omega 2, and omega 3 are. And that'll give me an idea for the axis for E1, the one that goes with lambda 1, which is 10 ma squared. And then I'll put in lambda 2. Well, it's going to be the same, so I'll get the same relationship between omega 1 and omega 2. And then I'll put in lambda 3. So let me get rid of this. So what we're going to have then is I find the relationship when I have lambda 1. That's going to give me an idea of what E1 should be. And when I go to lambda 2, it'll give me an idea what the axis for that moment of inertia should be. And then because lambda 1, this is the moment of inertia about the axis E1 when you have the principal axis. This is the moment of inertia about axis E2. This is the moment of inertia about axis E3. So let's go back to that. Boy, so let's move this up. I'm going to look at this. Lambda 1 was 10 ma squared minus lambda, so I'm going to use lambda 1, which is 10 ma squared. So 10 ma squared minus 10 ma squared is 0. This one was 0, 0 already, and that was 0. This was 0. This was 6 ma squared, so minus 10 ma squared gives me negative 4 ma squared. This was negative 4 ma squared already, so it just leaves that. This was 0. This was 6 ma squared minus 10. No, that was negative 4 ma squared, so that just stays the same. This was 6 ma squared minus 10 gives me negative 4 again. So that times omega 1, omega 2, omega 3 equals 0. So what equations do I get? Well, I get omega 1 plus omega 2 plus, the first one is 0. That doesn't help me much. This times that is negative 4 ma squared omega 2 minus 4 ma squared omega 3 equals 0. And this gives me the same one. So I only get one equation, and I need to find omega 1, omega 2, omega 3 that will satisfy this. So, and it's arbitrary. I can choose, I just need to satisfy this equation, which this tells me omega 2 equals negative omega 3, right? Well, and it needs to be a unit vector for E1. I could make omega 1, 1. There's no reason I can't, but if I did that to satisfy this, I could do this. So E1 is our x plus 0y plus 0z. That satisfies it. What else? What else satisfies it? I could use E1 equals omega 2 could be, omega 1 could be 0, because that's really arbitrary. Omega 2 could be 1, omega 3, negative 1. But then I'd have to put, to make this a unit vector, put the square root of 2, 1 over the square root of 2 in front. So that would work. So I could use, so I'm going to use this for E1, and I'm going to, because I get the same equations when I use lambda 2, remember? So lambda 2 is also 10 ma squared. So I'm going to use E1 for this. I'm going to use E2 is equal to 1 over the square root of 2, 0, 1, negative 1. So that would work. These two have to be perpendicular, and it looks like they would be, but let's check. E1 dot E2 is 1 times 0, 0, 0 times 1 is 0, 0 times negative 1 is 0. So that's 0. So they are orthogonal. So that would work. And then, now for lambda 3, for E3, I could stick in lambda 3, which was, what was lambda 3? I have it somewhere here. Let's find out. Let's stick in lambda 3 is 2ma squared, so it makes that 10 minus 2, 8ma squared. Then I get 0, 0, 0, and this was 6ma squared minus 2, so I get 4ma squared. This was still negative 4ma squared. 0, negative 4 minus plus or minus 2 is 6, negative 6ma squared. 6 minus 2 is 4ma squared. Okay, so I get 8ma squared omega 1 is 0. I get, again, 4ma squared omega 2 minus 4ma squared omega 3 is 0. And I get negative 6ma squared omega 2 plus 4ma squared omega 3 equals 0. So I need something that satisfies all of these if I did that right. Oh, this one should have been negative. It doesn't change. It's negative 4. So that's negative 4. So from this I get whatever omega 2 is has to equal omega 3, and let's make omega 1 is 0. So E3 looks like 1 over the square root of 2, 0, 1, 1 works. So there I have all my 3 now. If I go back to my original coordinate system, here's x, here is z, this was y. So now the new axes are E1 was 0, 1, 1, 0, 0. E2 was 1 over the square root of 2, 0, what did I say? Zero, 1, negative 1, and E3 is this. So let's look at those. E1 points along here. E2, I go 0 in the x, 1 in the y, negative 1 in the z, so that goes this way, where this is 45 degrees. And then E3, 0, 1 in the y, 1 in the x, so goes this way, 45 degrees. So there's the principal axes for those that rigid body that we had made up of 3 masses. So that's how you do it. With a little practice, it's not too bad. I'm going to give you another problem where you have a discrete set of masses. to do the same thing for some practice. All right, so next time I'm going to talk about what's called Euler's equations of motion for a rigid body. So to find the torque on a rigid body and the angular acceleration then if you can find the torque. Okay.